Hey, Jack, can you hear me? So,
Hi.
yeah, I'm at the airport, so I think I can only tune in for your first 20 minutes.
Okay.
Yeah, sorry for missing your talk. Yeah. Okay, where are you? Are you at your home right now?
Yeah, that's right.
Nice, nice. Great. Yeah. Yeah. So I will mute myself not to put too much background noise to your talk. Yeah. Okay. So SLAC still does not allow traveling. Do you know how long the policy will last?
This probably it's gonna last for a long time, I think. So I know at least one person went to Aspen. The trick, my mistake was I sent an email to Tom and the group secretary, and they of course said, no, you can't go. It's against DOE policy.
Yeah.
But the person who went to Aspen, also people from Fermilab too. The trick was not just, at least definitely not to say anything written.
Yeah.
Maybe ask verbally.
Yeah. That's the rule they told us. It's better to be, what's the word, apologetic than to be something else. Better be forbidden to do something in national labs.
I would really like to visit Minnesota.
Yeah. It's a pity that you couldn't make it due to the lab policy. Yeah. Yeah, but once the DOE people find out the national lab people are in Aspen, they are not supposed to. The people who are supposed to come in the following week are in trouble. They are not getting reimbursed, and they have to pay themselves.
But that actually happened.
Yeah, that actually happened. So, okay. Yeah. So. Yeah, so if you if you violate the rule, you violate it earlier than later.
How did they find out?
They actually receive messages from the lab saying, we saw on Twitter that lab scientists are posting photos.
You haven't?
Yes.
Okay, great. So yeah, thanks for having me. It's a pleasure to be visiting you guys, even if it's only virtually. Okay. Yeah, so the data that we get from the Large Hadron Collider is very complex. It's very high dimensional. There's hundreds, maybe thousands of particles in the kind of events that we're most interested in. And that's too complex for us to deal with directly. But because we understand a lot of particle physics, we know how to do effective dimensional reductions in this data set. Most notably, we know that the majority of these particles cluster in these collimated objects. So we do jet clustering. And instead of describing all the detailed remainder of all the individual constituents, we know we only usually need to describe the overall bulk properties of these jets. And so with our understanding of particle physics, we do a dimensional reduction of the data set. And our choice of dimensional reduction is a reflection of our understanding of how much information is actually, how much interesting information is actually present in an event or in a jet. I want to cover this from a different perspective, which is, forgetting about our understanding of the underlying particle physics. Can you look at this from a data science perspective? And just directly from looking at the data, infer useful dimensional reductions on the data. And then we can probe, do these dimensional reductions correspond to what we do as humans? Do they, or at the very least, do they do something that's that we can probe and understand, and we can see that it's doing something sensible? And so I'm going to explain to you how I've been training neural networks to do this kind of thing. And it's not entirely clear to me yet whether there's going to be practical applications in terms of really actually, deepening our understanding of particle physics through this. But I think my results are interesting in their own right, and my objective with this talk is going to be to convince you of that. And so there's not going to be so much in terms of detailed physics results. There's also not going to be much in terms of technicalities of neural network architectures and things. Instead, I'm going to focus on developing a conceptual intuition for what my neural networks are doing and why they do it and what they're coming to understand about the data. Okay, so I've organized this as a 7-course meal, and we've just finished the aperitif, which was this question of dimensional reduction and information content. And then I'll present the appetizer, which is going to be an introduction to this interesting kind of neural network called an autoencoder. And then I'll take a brief detour in the fish course to describe something that was introduced by Jesse Thaler and his students a couple of years ago, which gives a geometric interpretation of LHC data that's going to be very useful for the kind of things that I want to do. And then the main course is going to be this intuition building section on something called a variational autoencoder. And this is going to be based on just simple 2-dimensional toy example where we could plot everything and really try and understand everything in detail. And then once we've got our intuition, I'll then apply that to a physics application, a simple physics application, which will be WJets, to see what these variational autoencoders learn about WJets. And then if there's time, I'm not sure if there will be, I'll say a few things about a potential application in unsupervised classification. I haven't yet done this on a physics example. I only have the toy example so far. And then finally, the digestif is the conclusions. Okay, so the appetizer is the autoencoder, which is a kind of neural network that's designed to reproduce whatever it's given as an input, is trying to reproduce as close a copy to that as possible. So in this example, we're feeding a neural network an image of an apple. So it's some n pixels. Each pixel has an intensity in each color, and those are the inputs to the neural network. And the neural network outputs an image, and it's being trained to make this image as close as possible to the input image, where closeness is defined by, in this case, you can just take each pixel one by one in the apple, calculate the difference between the pixel intensity in the input image and the output image, square that, and then sum it over all pixels. And that gives you a measure of similarity between 2 pictures of apples, or 2 pictures in general. So in principle, all it has to do is learn the identity matrix. And the thing that prevents it from doing that is just that in the middle of the autoencoder, there's a narrow layer which can only convey a limited amount of information about the input. And so really, the last part of the neural network, which is called the decoder, is trying to infer from a limited amount of information what the apple looked like. And the encoder, which is the first part of the network, is trying to be as informative as possible about the properties of the apple in this limited space that's available in the middle. And so the kind of intuitive hope that one might have here is that this bit in the middle, which is called the latent space, encodes a reduced representation of the apple, quantifying its most important features. Is it red or is it green? How big is it? What's its orientation? Things like that. And maybe you can probe this latent code to actually learn about the space of apple pictures after you've trained your neural network. I just want to say one thing about again this notion of distance between pictures of apples. So really, this distance that I described of taking all the pixel intensity differences, squaring them, summing them, that's just a Euclidean distance, right? Each image, if it has n pixels, it's just for simplicity, let's say it's grayscale pictures. So it has n pixels, that's n numbers, and the difference between two pictures is literally the Euclidean distance between two n-dimensional vectors. And so one should picture these apple pictures as living in an n-dimensional embedding space, which is large, but the space of apple pictures actually occupies a lower dimensional submanifold in that space. And one wants to learn how to describe the properties of that lower dimensional submanifold. So in the particle physics case, I'll get to that actually in the next slides. So I want to use something like this for jets, for collider events, and to see if the autoencoder can learn something about particle physics in this latent space, and see if we can interpret something about particle physics from that latent space. For that, we need a distance measure between either entire collider events or between jets that corresponds to this pixel difference between apples. And
hi, Jack. This is Jen. I just have a trivial comment. Maybe you can confirm. So what this encoder does is actually I input an ensemble of different apples, right? So they encode the information trying to reconstruct. If I just give it one image, of course it knows how to perfectly reconstruct it, right? So it's really trying to compress the information of an ensemble of different apples into the latent space and trying to reconstruct them as much as possible. And the encoding itself has some probabilistic interpretation as well.
That's not accurate. So I am going to get to probabilistic later. This is not probabilistic. This is completely deterministic. Now, if you were to only train on one apple picture, so you initialize your neural network, you train on one apple picture, it's going to learn to reproduce that apple perfectly. But actually, you train on a million different apple pictures, and they're all different. And the latent space isn't expressive enough to express all the subtle differences between each and every apple. So after it's trained, you then give it one apple picture, and that apple picture isn't going to be perfectly reproduced because the latent space isn't expressive enough to encode everything about that particular apple picture that you gave it. It's only going to encode the bulk properties. Does that answer your question?
I think it clarified. Thanks. Yeah.
Okay. So yeah, we need some measure of how similarity between collider events that can be used to measure how well an autoencoder is doing at reconstructing collider events. And a nice candidate for this was introduced by Jesse Thaler and his students a couple of years ago. I want to pause this video. It looks like it's just going to play. Anyway, so it's called Earth Movers Distance, and it's the formula is given here. I won't spend too long on the details of the formula, but the idea is you input two events or two jets, and it outputs a number which is supposed to sorry? Is there a question? Okay. Yeah, so this Earth Movers Distance spits out a number that characterizes a measure of similarity or difference between the two events or the two jets that you gave it. And so what you should, let me see if I can figure out how to make this play again. Yeah, there you go. So yeah, so in this triangle, there's three different top jets, images of top jets, where each particle inside the jet is a point and the area of the point corresponds to the energy of that particle. And so these are three different top jets, and the side lengths of this triangle correspond to the distances between these jets calculated by this Earth mover's distance. And what you should imagine is you start with one of these jets and you want to smoothly transform it into another jet by moving energy around within the jet. And the cost of moving energy around in the jet is the energy that you're moving times by the distance that you're moving it. So each the specific way in which you move the energy around with the jet is a transport plan, and for any pair of jets there's an optimal transport plan which minimizes the cost of that conversion of one jet into the next jet. And the cost associated with that optimal transport plan is the Earth mover's distance. So it's the minimal cost for smoothly transforming one jet into another jet. So it has some nice properties. For instance, it's insensitive to collinear emissions and infrared emissions because a collinear splitting, the angle between the two daughters is very small, and so there's a small cost for converting one particle into two almost parallel particles. And similarly with infrared emissions, there's a small cost because infrared emission, soft emissions, just because the energy is small. Also, it has this distance satisfies the triangle inequality in that if you go from jet A to jet B to jet C, that is always a longer distance than going from jet A directly to jet C. Okay, so this distance, now that you have a notion of distance between events or between jets, it defines a metric space, and the set of collider events or the set of jets occupy a manifold in this space. So you can think of an embedding space, which is like the number of particles in your event times by 3 or 4. But the actual data only occupies a submanifold of that larger space, right? Top jets, for instance, mainly you only need to know about the relative angles and energy sharing between the 3 prongs to describe everything about the top quark. And then maybe you say a little bit more about the extra emissions, but you don't necessarily need 50, 100, 200 numbers. Okay, and this distance measure, I'm taking the slide directly from a talk that Jesse Thaler gave at SLAC a couple of years ago. Another nice feature about this distance measure is it encapsulates different physical processes at different scales. Whoops, I wanted to play this again. Yeah, so at the start you have a 500 GeV top quark just represented by the overall jet momentum of 500 GeV. And then you imagine the top quark decaying into 3 light quarks. There you go, splitting up into 3 light quarks. And the Earth mover's distance associated with that transition is around the top quark mass. And then there's quark shower, and the Earth mover's distance associated with the transition from the 3 quark state to the showered jet is around 50 GeV. And then finally, the quarks hadronize, and the Earth mover's distance associated with that transition is 30 GeV. So different physical processes are associated with different length scales in this space, which is interesting. I'm trying to convince you that you should think of this geometrically. If there's a geometry, there's notions of dimensionality. Of course, this is we're sampling events, and so we have discrete populations of events, and so there's a notion of dimensionality for these data sets, which is called the correlation dimension. So if you think about this data set here, which is this spiraling shape of dots, where if you zoom in, it's really 2-dimensional, as you see here. But if you zoom out further, it looks like a 1-dimensional line. Now, the correlation dimension, in order to calculate that, you consider balls or boxes of a certain radius, and you ask how many points are within that ball, and how does that scale as you scale the size of the ball. So if you zoom in really close and you look at balls this size, as you expand the ball, the number of points within the ball scales with radius squared. So the dimensionality at that scale is 2. Whereas if you take balls of this size, as you scale the radius of that ball, the number of points within the ball scales only as the first power of the radius of the ball. And so the dimensionality at these scales is 1. And the actual calculation that you do is you just take the derivative of the log of the number of points in the ball by the log of the radius of the ball. And so you can ask, what's the scale dependent dimensionality of collider events or of jets? And this is a plot taken again from their work where they look at top jets, W jets, QCD jets. And for top and W jets at around their mass scale of 100 GeV, there's around there's a 2-dimensional space for W jets. These are centered these are centered, I think rotated, I'm not entirely sure. But yeah, this corresponds to the orientation of the hard prongs within the W jet. And then the top jets are more complex. They have 5 or 6 dimensions corresponding to the orientations of the 3 quarks within the jet. And then as you look at smaller and smaller scales where QCD emissions and showering and hadronization become relevant, the dimensionality goes up and up and up as the scale goes. This resolution gets smaller and smaller and smaller. Okay. So I want you to think of collider events or of jets as in this geometric way. And what I want to do is probe the geometry, probe the geometry of collider events or of jets. And that's something that Jesse and his collaborators have been doing directly. I wanted to train a neural network to describe the geometry, and then ask how much can I learn about the geometry, not by looking at the data directly, but by probing the properties of the variational autoencoder that's been trained on this data set. Now, first of all, I want to go back and explain to you why I actually gave you a pretty terrible appetizer in the autoencoder, the regular autoencoder. It doesn't actually fulfill this role very well at all. And I have a very simple toy example that illustrates exactly why it fails. So I've generated data points in this 2-dimensional space on the left, according to this 2-dimensional Gaussian. So this is a 2-dimensional space, and I'm going to use Euclidean distance as my relevant geometric distance in this space. And I'm going to train an autoencoder to try and reproduce. You give it a XY coordinate from the input. It goes into the autoencoder. We've got a 1-dimensional latent space, and then it spits out another 2-dimensional coordinate, which would be these orange points. And it may not be at exactly the same place as the input was. And so the reconstruction loss that's being used to train this autoencoder is the Euclidean distance between the reconstruction and what the original input was. Okay, and does the autoencoder learn something interesting? Really, it doesn't. I told you the latent space is 1-dimensional, so I can plot a histogram. I take input events, I map them to the latent space of the autoencoder, and you get this histogram for latent codes. And then you decode those codes into the reconstruction space, and you see these latent codes. The latent code parameterizes the distance along this line. So every input point is mapped to a point along this line, and it's just going to be mapped to whatever point along this line is closest to the input. so the autoencoder is trying to learn some dense packing of the data space, but one can see that this is going to be highly coupled with the the details of the network architecture that you choose. If you make a much more powerful and expressive neural network, it's just going to pack this much more densely. You're not learning anything about the data set in this way. You're learning as much about your autoencoder architecture as you are about the data set. At least I don't see any way to learn anything interesting about the data set this way. But going back to what Jen brought up earlier, there's a variation on the autoencoder that is going to be much more useful for our purposes. It behaves in a much nicer way. And the key thing is inputs aren't going to be coded deterministically, but probabilistically. So for every input, instead of encoding deterministically to a latent space coordinate, you're encoding to a probability distribution. In practice, you're encoding to a multi-dimensional Gaussian with as many dimensions as there are latent space dimensions. So for 10 latent space dimensions, you'd have a 10-dimensional Gaussian parameterized by 10 variances. Oh, I thought I was using my pointer. Yeah, parameterized by 10 variances at the top here and 10 means here. And so I'm from that 10-dimensional Gaussian, say, if I'm using a 10-dimensional latent space, I sample a latent code. And then that latent code is then used by the decoder to try and reconstruct the input. And so just like with the autoencoder, there's a reconstruction cost. How close is the output to the input? But there's also this extra term that's associated with the parameterization of the latent space distribution. And what this term does is one can quickly show that this term is minimized if for every input you map to a standard Gaussian with mean 0 and variance 1 in every direction. And of course, if every single input is being mapped to the same standard Gaussian, then sampling from those distributions, you're not going to learn anything about the input. And so the latent code is going to be completely uninformative for the decoder to use for reconstructing the input. So this term discourages information being learned. It prefers that no information is encoded in the latent space. But of course, this term, the reconstruction term, prefers that information is encoded because the decoder needs to learn some information about the input in order to provide a good reconstruction. And so these terms are in competition, and it's the balance of these terms that's going to be critical for everything that I'm going to tell you about. And there's this hyperparameter beta that I put here, which is going to be important for determining exactly how this balance goes. And I'm going to spend a couple of slides talking about beta because it's super important. And this beta is something that you choose, you set, say beta equals 1, beta equals 0.1, you train the autoencoder. You can vary it if you like. Okay, and you can put this beta either in the denominator of the first term or in front of the second term. It's the same thing, it doesn't matter. But these two ways of writing it highlight two different complementary interpretations for what this beta is doing. But the first thing to note is that this beta is actually a dimensionful quantity. It will have the same dimensions as whatever the reconstruction error is. So when I move on to jets, this reconstruction error is the Earth mover's distance, which is units of GeV, in which case this beta will have units of GeV. And so that's one interesting thing. And this, so if we look at this way of writing the loss function at the bottom with the beta in front of the KL divergence term, this highlights beta's role as a cost of information encoding. So in the limit that beta goes to infinity, you're going to prioritize the second term over the first term in the training loss function of the variational autoencoder, which means that the autoencoder is being encouraged not to encode information. I told you that this term prefers that every input is mapped to in the latent space, a standard Gaussian. And so here, for instance, these two blue curves are two distributions encoded from two different inputs when trained with large beta. And these are completely overlapping distributions. And so samples from these distributions will tell you nothing about what were the details of the input. Whereas if beta's in the limit that beta goes to 0, the second term doesn't matter, and the first term is what the variational autoencoder will focus on optimizing. In which case, every different input sample is going to be mapped to narrow Gaussians along at different points in the latent space direction, such that samples from these Gaussians are very informative about which distribution it came from and therefore which input it came from. And when you talk about large or small beta, you have to compare it to something, and that something is going to be what are the relevant length scales in the data set that you're looking at. And we'll see this in much more detail shortly. Just to reiterate, so beta is the cost for encoding information. The encoder is only going to encode information about the input to the extent that its usefulness for reconstruction is sufficient to justify the cost. Okay. If I rewrite the loss function with beta underneath the reconstruction error, this highlights its role as a resolution. One finds that when training the variational autoencoder, this beta sets how smeared, how much smearing is done when you pass an event to the variational autoencoder. So for instance, if I were to train on this data set that I showed you earlier, and I import a point, say here in the middle of this green circle, and I train the variational autoencoder with beta that's given by the radius of this circle, then the output of the variational autoencoder is going to tend to be smeared over a disk of radius beta. And this is coming from the stochasticity of the sampling in the latent space. So betas are going to be also a physical resolution. Okay, so I want to give a two-dimensional toy example where we can understand everything that's going on, and then I'll move on to some physical examples. So I've generated, again, data in this two-dimensional space. Each blue point is a data point, X and Y coordinates. And I've generated this just from two Gaussians in the X and Y coordinates. And then I warped it so that it has a non-trivial shape. And the length of this banana shape is standard deviation is 1, and the width, the standard deviation is 0.1. So there's a hierarchy of scales of a factor of 10 between the length and the girth of the banana. And I'm going to train a variational autoencoder with a 10-dimensional latent space, which is way more than it should need, to take input points and try and reconstruct them as accurately as possible within that space. So I'm going to show you a few plots that show you what the neural network has learned. Unfortunately, I wasn't able to, I did this experiment about a year ago and I wasn't able to find the first plot that I wanted to show you, but it's a very simple plot and I've made the sketch instead. So what I do is I train the neural network at many different values of beta. So I train starting, say, beta here, and then once it's plateaued, then I train here, and then when it plateaus, I train there, and then it plateaus, I train there. And so I'm training at many different resolution scales. And on the y-axis, I'm going to plot the KL diversions associated with each latent space direction. So remember there's there's a KL divergence associated with every single latent space direction, and then you sum them up to get the total KL divergence. And so there's 10 lines in this plot, but 8 of them stay at KL equals 0. And since KL I told you was some measure of how much information is being encoded, that's telling you 8 dimensions are not encoding any useful information. But 2 dimensions come up above 0 at different scales of beta, which indicate that these 2 dimensions are learning information about the data set. And what I'm going to show you in the next plots is that the first line, the top line is the variational autoencoder learning about the length of the banana, and the lower line is the autoencoder learning about the girth of the banana. Okay. So first of all, I have the autoencoder trained with beta of 0.03. And I want to look at specifically these 2 latent space directions and what do they mean. And so in the middle plot, I have the gray cloud of points is the mapping of all the training data into the latent space, and it's this 2-dimensional Gaussian. And then I want to ask, how are these latent space directions mapped to real space directions? And that's what these plots are doing. So if I take this latent code, say here, at -2, 0, and I pass that through the decoder, it maps to this point here. And then as I go along this line and decode points along this line, that decodes to displacements along this line. And similarly for the light blue and the purple. So horizontal lines in the latent space in this latent space correspond to translations along the length of the banana. So one latent space dimension has learned the length of the banana. And these vertical lines map to these lines along the width of the banana. And so, yeah, the second dimension has learned to characterize the width of the banana. One can go a little bit further. So I have this plot in the top right, which shows on the x-axis the inverse of the mean of the encoded standard deviations in the latent space, which the KL time is dominated by the log of this quantity. And every point in this plot is a latent space direction. And there's 8 points here at 0, mean of 0, standard deviation of 1. And so they're encoding no useful information. Then these 2 points correspond to these 2 latent space directions. And first of all, we see there's a factor of 10 between these 2 latent space resolutions, which corresponds to the fact that the length of the banana is 10 times bigger than the width of the banana. You need, in order to acquire a specified resolution of a point in the real space, you need to characterize the fractional position along the length of the banana 10 times more accurately than the fractional distance along the length of the banana. And so that corresponds to the factor of 10 between the precision in which latent space coordinates are being resolved in those 2 directions. And you can actually infer both the length and the width of the banana by literally doing the beta that this is trained at divided by these sigmas, and you get roughly 1 for the length and 0.1 for the width. So maybe you didn't see, maybe you didn't look at the data in the first place. Maybe it was too complex because this banana is embedded in a 100-dimensional space and it's twisting around in that space somehow. And you wouldn't have been able to infer by eye what are the characteristics of the banana. But if you run it through this variational autoencoder, you get results like this, which show you that actually there's two relevant dimensions in this particular scale. One of them's 10 times bigger than the other one. Okay. Are there any questions about this? I'm going to move on to different length scales, but first of all, are there any questions at this point?
So, hey, Jack, you maybe went too quickly with the top right plot. Where do I see the factor of 10 difference? Am I comparing the first and second dot, or?
Yeah.
These
two dots. This dot is at around 4 and the 4 or 5 on the x-axis, and the second dot is at 40 or 50. And so the if you take 1 over that, so about 0.25 and 0.025, those are the standard deviations of the Gaussians that are being encoded in the latent space. And so, right, an input point is being encoded into the latent space with a variance of, with a standard deviation of 0.25 in one of these directions and 0.025 in the other one.
And I see, sounds good, thanks. Just curious, the upper right plot, you get that, you derive that from using a particular small beta, or you actually have to scan over different betas of various scales?
This is a 1 beta. I think beta is 0.03 if I remember correctly.
Yeah, just small enough, you resolve all dimensions, then you check what's the deviation in each latent space dimension, right?
Yeah, and what happens is if you change beta, if I start making beta gradually smaller and smaller, these points will move to the right, such that beta divided by sigma is constant. Yeah,
but their ratio between those 2 points wouldn't change, I think.
Exactly. That's always going to be a factor of 10 because the ratio between the respective real space dimensions is a factor of 10. Actually, this is a great question, because as you increase beta, these 2 points are going to move to the left. And at some point, this point here is going to come down here and join this point here. It actually follows a curve that comes down like this. And so that actually leads neatly into the next slide, where I've moved beta down to 0.3. Now the resolution is too big for the variational autoencoder to actually care about the width of the banana. Now it only cares about the length. It encodes information only in one direction, and it maps points along the center of the banana. So now we're looking at a one-dimensional data manifold at scales of around 0.3. And if I'd have shown you, I don't have the same plot as the top right here, but if I had shown you, this point would be down here and this point would be somewhere around here. And then finally, you can run it at large beta, and now the resolution is so broad that the variational autoencoder doesn't care to resolve anything about the banana. All the inputs are mapped to the average points, and the latent space is completely uninformative. We can see there's a notion of dimensionality at different scales in the variational autoencoder's latent space. I gave it 10 dimensions, and if I'd have done that with a regular autoencoder, it would have just used them all in some arbitrary way. But we see with the variational autoencoder, this fact that we're encouraging it to be maybe something I should have emphasized more earlier is that, this balance between the two terms, what it's doing is it's telling it to try and be as parsimonious as possible with encoding information. Uses encode as little as possible, only what's necessary for the objective of reconstructing at a particular resolution, and no more. And the consequence of that is that it learns to use an appropriate number of dimensions that correspond to the actual dimensionality of the problem, depending on the scale at which you're telling it to learn at. That's how. The reason is that that's the most information efficient way of describing the coordinates of the banana. And so that because of this requirement to be efficient with information, is learning a representation of the coordinates of the banana that corresponds to the kind of coordinates that we might use, because we also like to be information efficient. So this toy example is what really like made me start thinking, okay, what's going to happen if I train on jets? What's an information efficient description of substructure, for instance? Okay, so I'm not going to spend too long on the slide, but one can try and quantify in more detail the dimensionality of the line representation. So I already told you about the correlation dimension, which is measured not on the variational autoencoder, but on the data itself. I realize now I actually wrote this incorrectly. It should be d log n by d log r. So this was the one I showed earlier, where n is the number of points within a ball of radius r. And then actually I want to, I've defined these two notions of dimensionality of the line representation of the autoencoder. I'll start with D2, where I take the derivative of the KL divergence with respect to log of beta, which if I go back to the previous slide, each of these lines is a straight line. And actually these lines have gradient 1 exactly. And so if you sum these gradients, you get 2 here, and you get 1 here, and you get 0 here. And so that gives a notion of dimensionality. And it actually has some similarity to the correlation dimension. If one thinks of this beta as a length scale, which corresponds to the radius of the ball in the correlation dimension. And then recall, again, I said this should be log n, not n. This inverse sigma is like a density. It is also like a number of points within a ball. And so this formulation of D2 looks a little bit like that, at least qualitatively. Writing it this way with KL as as a measure of the information being encoded, this gives the scaling of information with resolution, which is some notion of dimensionality. So that's how I define D2. And in particular, so I train the neural network at different values of beta. I train it at 1, I wait till it's plateaued, and then I change beta a bit and keep training again, and the neural network shifts. And then I train it another beta, and then I take the derivative with respect to these different neural network iterations. And then this D1 is a derivative of the reconstruction error with respect to beta squared, which I can prove in the simple case that I'm training on literally Gaussian data. I can prove that these two are equal. They're not going to be equal in general, but the intuition behind this is that right. So when you give an input to the variational autoencoder, you output and you do that, say you do that, say 100 times, and you get 100 different points that are scattered in a ball in the vicinity of the original point. The scale of that distribution is going to be given by beta, but it's in some n-dimensional space, and so the reconstruction error is d times by beta squared, where d is the dimensionality of that space. Right, because you sum uncertainties in quadrature in all the directions, and so this derivative brings out the d that you get from summing all the individual uncertainties in all the directions, and so they're not in general intrinsically related. I only know that they're related intrinsically if you're actually dealing with truly Gaussian data. But anyway, I plot D1, D2, and the correlation dimension as a function. This length scale is beta, and I get dimensionality of 2, 1, and 0 with the various scales. That maps roughly to the correlation dimension. I've not seen these formulae before, They make a lot of sense to me. I've been looking to see if people have talked about this before, and I haven't seen it. Yeah, so I'm not sure whether this is new. I think it might be. Okay, I'll skip that. Yeah. Okay. It should be application to WJets. So, okay, I'm going to train a variational autoencoder where my inputs are phi vectors for 50 particles. I pass it through some encoder, the details don't matter. And then it goes into a large latent space, like 300 dimensions, larger than the size of the input. And then it goes to a decoder, and you get 50 particles on the outside. And you measure the earth mover's distance between the input jets and the output jets. In practice, I use an approximation of the earth mover's distance just for technical reasons. It's how I found to train the neural network, called the sinkhorn distance. The details aren't important. So I'm just going to keep calling it the earth mover's distance. And I train my autoencoder at many different values of beta. Yeah, ignore, yeah. This beta, yeah, there's beta, which is the dimensionful beta. In practice, when I train my neural network, I rescale the phi vector inputs so that instead of momenta being hundreds of GeV, I scale it so that the overall jet momentum is 1. So I have a dimensionless beta corresponding to the rescaled inputs, which is the y-axis on the left. And so, I train the neural network with 10 to the minus 5 beta, then this, then this, then this, then 10 to the minus 4. So this is called an annealing schedule. I train at many values of beta. And what happens is as I increase beta, the neural network is learning to encode information more and more efficiently. And then as I reduce beta, it's learning new information, but not necessarily efficiently. And these repeated cycles of beta going up and down, encourage the neural network, on the one hand, to learn new stuff, and then on the other hand, to organize it in an information efficient manner. And this is called annealing. And then I'm going to show you results corresponding to this last run after it's finished training. So yeah, to repeat, at each point, I train the neural network until it plateaus, and then I move to the next point with the same neural network. I train at the new beta until it plateaus. And the next point, train it until it plateaus. Okay. And first, some summary statistics. I train on both uncentered WJets and uncentered WJets. We see so that each of these lines is associated with one of the roughly 300 latent space directions. And the y-axis is the KL diversions associated with each of those dimensions. So it's how much information is being encoded in each direction. And on the left-hand side, for very small beta, things are a bit messy, but for intermediate and then large beta, we see that information has been organized into a small number of latent space directions. And I'm going to show that the first two here corresponds to the eta and phi coordinates of the overall jet for the uncentered jet. And then the subsequent dimensions describe, first of all, the orientation of the two-pronged substructure within the jet, and then subsequent QCD emissions. We see that for the centered jets, the structure is somewhat richer here than here. And that's because it's just because my neural networks aren't really expressive enough to learn everything from the overall jet momenta down to all the very detailed jet substructure. So with the centered W jets, the neural network has a much easier time and is able to learn this structure in more detail. So what I'm going to do first is show you how the VAE learns the overall bulk properties of the jet when it's uncentered. And then I'm going to move on to centered W jets to show you what the VAE learns about the jet substructure. Okay, And before I move on to that, I have plots of the dimensionality of the VAEs as a function of scale. So for the uncentered W jets, we have a two-dimensional representation between over around 1 order of magnitude, because so the momentum of these jets is around 500 GeV. The W jets have a mass of 80 GeV. So there's roughly an order of magnitude over which the jets are two-dimensional. They just have either and phi coordinates. And then they get higher dimensional because you have the two-pronged substructure. And then they get higher and higher dimensional as it learns more of the QCD junk. And we see that the centered W jets, the VAE has a better time learning the QCD stuff at smaller scales compared to the uncentered one where it messes up. Where these two lines, the orange and blue, it's the two dimensionalities, D1 and D2, that I defined earlier. I just want to make one comment, which is that if I go back one more slide, we see over here, there's these two dimensions, which I'm going to show you are literally eta and phi of the jet. And there's this other one here. So it looks like it's three-dimensional here, but it's actually two-dimensional when you calculate these dimensions that I defined. And that's because, while this line has gradient 1, this line has a much smaller gradient, and so it doesn't contribute to the dimensionality. I'm going to show you right now what's actually going on there. So, okay, there's a lot to unpack in this plot, but what I have on the left is a grid of points within the latent space, within the first two most important directions of the latent space for the uncentered W jets. So at every square in this plot corresponds to the latent space point associated with the center of the square. So this square in the middle corresponds to the latent point 0, 0. This one here corresponds to something close to 1, 0, 2, 0, 3, 0, etc. Okay, and the blue contours in the background indicates the support from the training set. That is, when I put training data through the neural network, the points are mapped to this region, which is a Gaussian of width 1. So if you depart from this region of support, you're actually going into unphysical regions where the neural network is actually doing an extrapolation. So one should be focusing on the region covered by the blue, and a darker blue is higher density of training points. Okay, and at each grid point, what I do is I pass that latent code through the decoder, and I get a jet out of it. And when you zoom into the jets, they look like this, because I'm training with beta of around 200 GeV. So it's not going to learn the substructure of the W's, but it is going to learn the eta and phi of the jet, and it just gives you an average W jet. So each little square has an embedded set of coordinate axes, which are just eta and phi coordinates within the detector. And each red point is a jet image. So here at Z0 is 0, Z1 is 0. That maps to a jet at the center of the detector. And then as I move left and right along Z0, the corresponding jet shifts in eta. So here, eta is around -3, and here eta is about +3. So Z0 is directly related to eta. As you move along Z1, the jet moves from left to right within the detector. So Z1 corresponds directly with the phi coordinate of the jet within the detector. Now you see that it doesn't go all the way around the detector, but that's what this Z2 does. So if we look at the right plot, we have Z1 and Z2, which are the second and third important latent coordinates. And Z2 acts as a categorical variable that just gives you like the sign plus or minus of the cosine of phi, right? So it just tells you whether it's on the left or the right side of the detector, say. So as you go around this loop, you do a full loop around the phi axis of the detector. You see this red point goes left, left, and then left, 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 and it does a full 360 loop. And you see the support, this blue curve is actually one-dimensional submanifold in this two-dimensional space. So it's learned still a two-dimensional representation of the data. It's just used 3 numbers to do it. This categorical variable, it's not like a true dimension. So this categorical one is this shallow gradient one. So it's, if one uses these notions of dimensionality, it still is a two-dimensional representation. It's just embedded using 3 numbers. Okay. I'm going to move on to substructure next. I wanted to pause and ask if there's any questions about this. Okay, so now I want to show what the neural network has learned about jet substructure. So I'm going to take, just because it's a bit clearer, the variational autoencoder trained on centered jets. And since each jet is centered, the jet images in this grid, they're centered jet images, and so the internal coordinate axes have a size of going from eta and phi from -0.5 to 0.5. So these are radius roughly 1 jets. One sees that right, as you move around in this latent space, the decoded jets, they're 2-prong jets, and as you move in different directions, those 2 prongs rotate, or the energy balance changes. So for instance, if we travel along this line here, we have energy balanced 2-prong jets, where as you travel along Z1, it rotates 360 degrees. Whereas if you say travel along this vertical line, all the jets have roughly the same orientation, but what's changing is the energy sharing. Here, almost all the energy is in one prong, then it becomes equal, and then almost all the energy is in the other prong. And I've indicated, these aren't calculated, these are just by eye, contours, red contours of energy sharing Z, which corresponds to the polar angle of the W decay. And the black lines are contours roughly in phi, the angle of the 2 prongs. And this maps directly to the the underlying geometric structure of W decays. So when a W decays in its rest frame to 2 identical particles, it's characterized by 2 coordinates, of course, phi and theta. Theta mapping, when you go into a boosted frame, theta maps to the energy sharing between the 2 prongs. And so it looks like it's topologically a sphere, but actually, since these are identical particles, so this is a W at the center decaying into 2 quarks, two identical particles. There's an identification of opposite points in the sphere because right, if you switch the 2 particles, you have exactly the same decay. And so actually the topology of 2-party decay of a W boson is RP2, the real projective plane, which one way of formulating it is is a sphere with opposite points identified, and so that's a double cover. You can represent that just with a hemisphere, which is almost a single cover, except you still have an identification of opposite points on the rim. So this pair of latent space coordinates is just a projection onto this hemisphere of the 2-body decay kinematics of the W, where the pole here is this point, and this is the equator, roughly, of the hemisphere. And the identification of opposite points in the sphere survives. Like you see, this point here on the left is identical to this point here on the right. This point in the bottom right is very similar to this point in the top left. So there's an identification between opposite points in the space. So even though the topology of the latent space doesn't quite match with the true topology of the data manifold, it learns a very good representation of that topology. It's not too much of a barrier, the fact that the topology differs. It finds a way of doing that representation. We saw it similarly also before with the eta and the phi. That's not a topology of R2, it's a topology of a cylinder, and it found a way to represent that cylinder. Okay, I'm going to go quickly now because I'm over time. But if you look at subsequent dimensions, it starts describing QCD emissions within the jet. So here I'm looking at the next 2 dimensions, and these 2 dimensions describe so the vertical dimension describes the strength of a third emission within the W jet. So here at the very bottom, there's no third emission, it's just a 2-prong jet. And then as you go up, there's a third emission in the bottom right that becomes more and more prominent as you go up. And it's the same in any vertical line. As you go horizontally, that's describing the jet boost. I should have said these jets are simulated with PT between around 450 to 550 GeV. So there's a PT width of around 100 GeV, which is comparable, of course, to the W mass. And so the overall boost of the jet is also described at roughly the same scale as the 2-prong substructure. And so on the left, these are 2 prongs far apart, and on the right, they're close together. And then the final one of these that I'll show is this one, which just describes the orientation of the third emission within the jet. So if you look at, say, a circle around here, this third emission is rotating. So there's these 2 large prongs which stay roughly fixed, and then the third emission is moving around the jet. So this is just describing essentially the X and Y coordinates of that emission. I'm going to skip the dessert because there's no time. You can ask questions if you like, but it pertains to like what happens if you have mixed samples instead of pure samples. So the variational autoencoder has learned how to represent the data in a hierarchically organized fashion. It's learned a dimensional reduction, and you can see like, oh, this one's the most important, this one's the next most important. With respect to and we didn't start with much physics, we just started with a distance measure that has physically interesting properties. And then the variational autoencoder learns the structure of the data set with respect to that distance metric. Part of the reason that I'm unsure whether this is actually going to have practical applications is just because we're really good at particle physics. We already know a lot of particle physics. This is like really great if you have a complex data set that you know nothing about in the first place, and you could really infer a lot of things about the structure of the data set. Whether actually this is going to give maybe some extension of this is going to give quantitatively precise enough to actually tell us things, it's not entirely clear to me. But I hope I've convinced you that it learns things that correspond to the way, in some sense, that we see things, and that is trying to be information efficient in this description, and so are we. Okay, that is all. Thank you.
Thank you. Let's thank Jack for the next talk. So is there any question from the audience? Let's see. You guys can speak up, but I see Roger, you have a question?
Yeah, hi. Thank you for the nice talk. There are some things I'm coming from this from a very different direction, since I work on one of these large collider experiments, and we have to worry about the data and try to squeeze out as much information as we can from the data that we have. So this is clearly pointing in that direction. One of the things when we use machine learning, BDTs, GNNs, CNNs, and all that stuff, is to separate out, well, first of all, to identify and classify particular classes of events, and then to separate out interesting physics from background physics. So did you, I mean, you focused on jets and Ws, which is, of course, an interesting subject, but if I were to take this approach and apply it in a real context where I have things like minimum PT for the tracks and all that sort of stuff, and where I'm no longer sensitive and I have errors in my measurements and so on, can this be turned around so as to separate out real events or interesting, exciting physics from plain vanilla QCD stuff?
Yes, that's actually what the slides that I skipped over is about.
Okay.
It's something that I have not yet applied it to particle physics data. It's something that I've been meaning to do for a while.
Yeah.
But I did play around in the toy example. And so, yeah, let me quickly go through that. So,
okay, just a minute. Okay.
Or do you have another part of the question?
Well, no, I have to leave to teach very quickly. So, okay.
Well, let me just quickly say that there's a variation where you add categorical dimensions, because LHC data has categories, there's different classes of events, and each of those classes are described differently. And so you can extend this and add categories and conditional inference, and it actually, at least in this toy example, I have two sets of data, one which is effectively one-dimensional, one which is two-dimensional. And I trained it unsupervised on this data set. And it actually learns that there's a one-dimensional component and a two-dimensional component. It learns to do with the classification, and it just learns to describe those separately in ways that are appropriate for those components. And so plausibly, this could be used for unsupervised classification, where you train it on a mixed sample of different classes, and it learns to do the classification. But
the sample would be construct. So you would do the classification ahead of the training, or
no. So you train it on unlabeled events.
Okay.
So this is the training set that I've given it, and it's literally just these points in this two-dimensional plane. And we can see by eye that there's these two distributions that are overlaid. But when I train it, I'm not actually telling it those classes. It's completely unsupervised. All it's got is these data points, and it's going to try and learn what's the most information efficient description for this. And the most information efficient description is if it lives along this line, you only need to give it one coordinate, really. So first of all, you say, is it on the line or is it in the bulk? If it's on the line, then you give one coordinate. And if it's in the bulk, then you give two.
Right. So ahead of time, you tell it what the target is. So the main part of the training is you give these two targets.
No. You don't give it. You only have distances. You only train it on distances. I'm telling you. So yeah, I was just trying to describe why. So this is going to be completely unclassified, unsupervised. You only have these data. You only give the neural network the data points and X and Y coordinates. You don't give it classes. And you ask, and I want to, without spending too long, explain to you why it figures out that there's two classes. And it figures out that there's two classes in the same way that we would figure out that there's two classes just by looking at this data.
Okay.
We don't need labels on these points to know that there's two classes. We can just look at the data and see it's immediately obvious. And if we were to try and describe this data in the most efficient way as possible, like using as few numbers as possible, we'd say, okay, there's two classes. One class lives in a line, it only needs one number. One class lives in a two-dimensional space, it needs two numbers. And so we describe it in that way. And what I'm trying, what I want to tell you is that the neural network does the same thing. We don't tell it there's two classes. It just sees two classes is the most efficient way of describing this data.
Understood. So just put it from that point of information. Okay. Right. Well, have you spoken to your colleagues there at MIT on the send the LHC experiments.
So I'm at SLAC, and I'm actually a particle physicist. I'm a theoretical particle physicist.
Okay.
And I have tried it with experimentalists, and people are interested. I'm going to, the first thing I'm going to do is something simple. I'm just going to look at W's and tots and have a mix sample and see if it does. And then I try and go on to more realistic examples. Now, if you want to actually find BSM physics, I'm going to try it on that, but the difficulty is, of course, BSM physics is going to have a much lower statistics, and this will need high statistics to actually learn. So I don't know in practice how useful it will be, but I want to probe that.
Right. Okay, well, thank you very much.
You're welcome.
SLAC, by the way, is on Atlas, so you can talk to that.
Thanks. So Jen, go ahead.
Hey, Jack. Thanks for a nice talk. Actually, my flight is delayed by 40 minutes, so I can't finish listening through your talk. But I'm on the airplane now. So good. Very nice and very intuitive. I just have two questions. One is about where you define your D1, D2 and compare with the correlation dimension D. Okay. Can you go to that slide? I find your definition very intuitive, as we discussed before. But what's this D correlation? Is that a meaningful quantity, this dashed line, or just because it's a traditional quantity we put it there? Although it looks like smooth, but it doesn't seem it doesn't seem to be sharp, right? It's this D correlation.
Yeah, I think what actually happens. This doesn't quite answer your question, but so the more Gaussian-like is the data, the sharper are these D1 and D2. But if in fact the data is sharp, if this was drawn from a square distribution instead of Gaussians, then the correlation dimension would be sharp. The VAE dimensions would be smoother. I introduced this correlation dimension all the way back here.
Yeah, I recall
this. In this sample, you'd get sharper jumps because this data looks sharper. But the VAE on this, you'd get you'd get two directions, the length and the width, but it would be those D's would be more blurred, I think.
Yeah, thanks. Another question is this: you seem to do a fancy training process where you vary beta going up and going down. Can you go to that slide? So it's a very complex protocol that you design. Is the sole purpose for this is to stabilize the latent space into a particular direction so you get some interpretable results, or why do you do this procedure, right? In principle, I can just train one for a particular beta, get some results, and vary it, right?
It is actually important. Now, the details don't matter, but this idea that you go up and down, this annealing process, it is important, because what happens on this first run, it learns a decent reconstruction, but it's not organized in a nice way. What actually happens, different physical processes come in at different scales. And the VA only learns to organize information efficiently when beta is at roughly the scale of the new information that's being learned. When beta is much smaller than that scale, it doesn't have much impetus to learn efficiently. And so, the reason for this annealing, the intuition that's happening is that as you're passing over new scales, it's kind of, smoothing those scales out and representing that efficiently. So it's super important. If you just learn at one beta, you don't get the results that I show. And I think that's why other people aren't showing these results, because they usually just train at one beta, and they say, oh, I'm interested in beta is 0.1 because that's that gives the best results for my objective, which might be a classification problem or something. But I'm saying, actually, if you smoothly change beta and study how the learned geometry evolves with that, it reflects the underlying physics in interesting ways.
I think I've quasi understand what you're saying. I'm confused why your last few iterations goes up, seems to be going to infinity. What's happening there? So I stabilize my network, and I reach some minimum, right, and the stable representation. Why the final iterations goes up?
Are you talking about this here?
The last line, the last diagonal line.
Yeah, this is just, so the y coordinates is just the beta that I'm training at. And what I want to be able to generate plots like this, where you know, I look at how the KL divergence varies with beta. And I want to do that after, you know, once I've had a well-trained neural network. So here, once I get to this point, I say, okay, the neural network is trained well enough. It's learned to organize the data well. And now I train here, etc. So in order to get the data points that I can put into these plots.
Okay, so that's the last readout session in some sense.
Exactly.
Okay, good.
Yeah,
good.
and that readout session is what's telling me, yeah, how is the representation varying with scale?
Okay. Okay. Thanks.
All right, thanks. Any more questions from the audience? If not, let me pause the recording.